Okay, so today we are very happy to have Michael Hastings from Microsoft, who will be talking about quantum cellular automata. Yeah.
Good, thank you. So I'll be talking about quantum cellular automata, but don't read too much into those words. It's commonly abbreviated QCA, and the words quantum cellular automata don't really mean anything. It's just sort of some historical artifact that they're called that. And I would really like to encourage people to see like 6 people walking in here, so even more walking in. Like it says somewhere. Horrible. So I'll be talking about QCA, quantum cellular automata. And I really want to encourage people to interrupt with questions because I don't exactly know what the background of everyone is, and I'm kind of used to talking about this to people coming from either condensed matter physics or quantum information theory. And so I want to try and give more of a motivational overview of why we study some of these questions. And so really, please ask questions and interrupt. So in physics, just to give some motivation, the study of phase transitions and phases of matter is one of the central areas of the field. So if you think about, historically, just look around you, there's like water and ice and steam are different phases of water. And if you go through a phase transition and you can turn from one to another, you can freeze water or boil water. But something you notice though, is that if you take some water and you put it under pressure, then the temperature at which it changes to steam, the temperature at which it changes to steam, at which it boils, will change depending upon the ambient pressure. And you can actually tune the pressure to reach a point where it can go continuously from water to steam without actually any phase transition happening. You can have that transition happen continuously. On the other hand, going from water to ice, there is no way to do that transition continuously. And the reason is that there is a broken symmetry between in the solid phase. In the solid phase, there's a broken symmetry that if you know where one atom is, you have some idea of where another atom very far away is likely to be. You have some long-range correlation, some breaking up the translational symmetry. And this has been a paradigm in physics, this Landau paradigm, that phases of matter are distinguished by broken symmetry. So a ferromagnet may break some symmetry to rotate or flip magnetic spins or something like that. So this has been for a long time the paradigm in physics, but then it became realized that there were more phases beyond this paradigm, that there were phases that were non-trivial, but that were distinguished not by any kind of broken symmetry. Even if you did not impose any symmetries on the Hamiltonian, there was some non-trivial symmetry present. And I want to talk about, actually, I'm going to just very quickly sketch sort of 3 examples of these phases, because these are all going to play a little bit of a role in relating to QCA and why we talk about QCA. So one of the first phases that I'll talk about is, just to give an example of a so-called topologically ordered phase, would be exemplified by a Hamiltonian such as the toric code Hamiltonian. So you have a lattice and in 2 dimensions, and you have some, we can draw as a square lattice, it doesn't really matter. And on each of these edges, you have a degree of freedom, a single degree of freedom, a qubit, so it can take 2 states, spin up or spin down. And you could imagine coloring the edges in which the qubit is spin up. And you have some terms in the Hamiltonian. One term lives at every vertex, and it penalizes states where sort of this ends. It wants you to have closed loops. So it's happy having a closed loop like this, but if you just have an endpoint somewhere, there's a penalty term at that vertex. A second term in the Hamiltonian lives on any plaquettes, and it gives some dynamics to these closed loops, allowing it to move from here, for example, over to here, and so on. So the ground state winds up being some gas of these closed loops. And this is an interesting Hamiltonian. It has some interesting properties. One property is that if you look at the excitations, it has some excitations that are anyons. They're non-local excitations. So you might have a long string that goes for a very long distance and ends in 2 points. And as I said, there's some energy cost to the string ending. But these must come in pairs. You cannot have a single endpoint to the string. So even though the one endpoint looks like a particle, that particle can't live on its own. There needs to be another one far away. And similarly, just like there may be defects in this thing that imposes that the string is this vertex operator, these plaquette operators also may have defects. And defects in the plaquette operator produce some phases for these. So there's actually a separate kind of excitation. This is one kind of excitation, an electric particle. There's another kind of excitation, a magnetic particle, and these two braid non-trivially with each other. One of them moves around the other, they pick up phases. So this phase is the torque code, and it's topologically ordered. One way of seeing that it's different from normal phases of matter is that when you look at this phase on a two-dimensional manifold that has some interesting topology, it may acquire a ground state degeneracy. So the degeneracy of the ground state will depend upon the first Betty number. So if you put it on a torus, for example, the ground state degeneracy of the manifold will be bigger than of the Hamiltonian will be bigger than 1. On a sphere, it will have ground state degeneracy of 1, but on other manifolds, the ground state degeneracy goes up depending upon the topology. So this is one kind of thing, and this is, we would say it's topologically ordered and has anyons. Let me talk about another phase that's topologically interesting, but does not have any anionic excitations. And this is another phase of matter. So we're going to imagine a one-dimensional line, and at every site, we're going to have a single Majorana degree of freedom. So for each site, we'll have some operator gamma I, and what are these operators gamma I? So these operators gamma I form some algebra operators on different sites anti-commute with each other, and they're Hermitian operators that square to the identity. So we can write gamma I J is 2 delta I J. And you can think of, if you have a pair of these Majorana operators, this really means that there's a freedom to have either a single, like we normally think of like electrons as particles. It's sort of like there could be a particle present or absent, but this is a more general way of decomposing the possible operators. And you can imagine two possible Hamiltonians on this. You can imagine many, but there's two classes of local Hamiltonians you might talk about. One Hamiltonian is going to look something like this. H is I squared minus 1, so it's useful to put that in front to make it Hermitian. Sum over J, gamma of 2J, gamma of 2J plus 1. So it's sort of a pairing of sites. So like site 0 with site 1, site 2 with site 3, and so on. And what that winds up doing is you're making something that looks like we'll draw little bubbles to indicate the sites that get paired by these terms in the Hamiltonian. It puts these two into some definite state, forces these two into some definite state, and it has a unique ground state. But of course, since you can write that down, you could also write down a different Hamiltonian where it's gamma of J plus 1, gamma of 2J plus 2, like that. And that would be paired in a way that's shifted 1 over. And these are sort of some model Hamiltonians, but they actually describe a meaningful physical setup in one dimension. One would be the state of just a one-dimensional wire that's in an insulating state. The other is a state that could be produced in a one-dimensional wire with strong spin orbit coupling, superconductivity, magnetic field, all these ingredients present, and you can produce something that looks like it's in the shifted phase. And why, but when you look at them, they seem like almost exactly the same. Like, what is the meaning that I'm sort of emphasizing that these are two different phases, and yet it seems quite so arbitrary what the distinction between these is. Well, in a real finite, if you talk about a real finite physical experimental system, it will have a certain number of sites like this. And in one case, you'll be left with some unpaired degrees of freedom at the end. And in the other case, you won't have these unpaired degrees of freedom at the end. So when you put them in a real degree of freedom, real physical system, there may be some distinction on the boundary. So there's some distinction between these phases. One phase is a trivial phase of matter. The other phase is what we'll call it non-trivial phase of matter. I'll make that trivial for themselves in a second. And here, though, if you put it on a closed manifold, in this case, the only thing you can put it on is a circle, there is no distinction. They both have a unique ground state. They both have the same number of ground states. If you want to talk about the nice thing here is there's some connection to, people in the field keep talking about these things as topologically non-trivial. There's some kind of obvious connection to topology that the ground state degeneracy depends upon what you put it on. Here, in order to probe some property of it, you can imagine this thing on some space-time manifold, and it will pick up a phase that, in this case, in the trivial phase, well, there'll be sort of some local junk, perhaps, depending upon just your actual physical realization. But then there's some universal phase, which for the trivial model will just be 1, but then for the other model will be some e to the I pi integral of W1 squared over this space-time manifold. So when you put it on some non-trivial space-time manifold, it can pick up some phase that detects whether you're in the trivial phase or the non-trivial phase. Questions up to this point? Everyone seems happy. Good. Okay. So these are kind of two paradigms. And this class of states here is an example also of what we call an invertible state of matter. So let me first talk about, well, first let me say a way in which we say that this is a non-trivial state of matter before we say that it's an invertible state of matter. So often the kind of equivalence of two states of matter we want to talk about is equivalence under quantum circuits. So if you just took this Hamiltonian and you said, oh, okay, but I want to look at the one where, I apply some, maybe I just map it to like these are paired and these are paired. It's really not, should not be distinguished. So in general, we'll talk about two states as being equivalent if you can write some quantum circuit. So what is a quantum circuit? So it's easiest to draw in one dimension. In higher dimensions, you imagine some gate, which is just some unitary. It may act on 2 sites or it may act on 3 or 4, but order 1 sites. You'll have several such gates. So they act, as I said, on site in parallel, and then you'll have some number of rounds of these gates, kind of like bricks layered on top of each other. And each of these gates will assume to be range order 1. The depth of the circuit will assume to be order 1. And we'll regard two states as being equivalent if they're mapped into each other by a quantum circuit. We'll say a state is non-trivial if it cannot be mapped back to some reference trivial state, such as that one, under a quantum circuit. So let me just quickly argue that this state cannot be mapped to that one under a quantum circuit. So suppose it could be, hypothetically, suppose it could be someone came up with some very clever quantum circuit that mapped this state to this state. Well, if it could be, what you could do, and of course, we should imagine that, I should say the setting is that we imagine that all these systems are very large. You can do it in 2 roughly equivalent ways. One is that you work really on an infinite lattice. The other is that you work on a sequence of finite lattices of increasing size, and you want everything to be uniform in size. So you have this putative circuit that maps this state, extended out infinitely this way, into this state. And you just truncate the circuit somewhere. You say, okay, I'm going to keep having the circuit doing whatever it is out here, but out here, I'm just going to end the circuit. I'm just going to cut it off and get rid of all the gates out here. And over here, just do the identity transformation. So I don't really know what happens in between because that will depend upon whatever circuit was made. But whatever it does out here is just the identity transformation. And whatever it does out here is this. So somehow it maps the state to something that has, this, this, and then it has an odd number of sites. I'll draw 3 just to draw a small odd number. And then it has that. And somehow it puts some state on this that's going to be some, or we'll map the Hamiltonian in some way that you'll have some unique state on here, but this is some unique ground state of this Hamiltonian here, but this is not possible because you have an odd number of sites. There's no way to get a single unique state on there. So this is sort of the sketched argument that this one is non-trivially related to them.
I think the way you've said it is oversimplified. You would have to somehow say that operators there couldn't commute with the others. Because if I take what you said literally, you have 3 gammas there. And 3 gammas can be given a 2x2 representation. And with the unique state. So you need to somehow say that you don't want to, that you need to have enough structure here so that you aren't able to use the 2-dimensional representation of those.
Yeah, I know. That's why I kind of like sketched and said, well, what we really should say is that you take this Hamiltonian and you will get something, you can map the Hamiltonian through, and what you'll find, I can do it more. The more careful way to do it is to say that we map the Hamiltonian through and we'll get something that's this Hamiltonian out here, something in here, and then perhaps some complicated Hamiltonian in here, but whatever complicated Hamiltonian we get here has the same ground state as this one. So we will wind up getting, so we can then start throwing out the terms of the mapped Hamiltonian here. And so we'll get some Hamiltonian on this odd number of sites that has a unique ground state, which we'll not be able to do using the allowed terms we can write. So these two states are distinct from each other in this way. Now let me mention one last.
Sorry to interrupt you, but perhaps
Sure.
you could phrase the argument as well. You'd have the three Clifford generators there,
Yes,
and the one on the left that you didn't touch. So you'd have four. And then in,
the one on the left. Oh, you want to complain that you want to say, well, there really is another site out there.
you're going to need to use that.
Yes, you're going to need another site out there, but you would then have to write down, in order to gap it, you would have to write down some term that involves this and this. But I can't because
Because it was supposed to commute with that operator.
I can't because I wrote down a local map. This isn't an arbitrary. One thing I know that this circuit does is that it's local. So there's no way I could have produced a term.
I thought you could have argued that the fact that the Hamiltonian has to commute with that operator keeps it from having a non-degenerate spectrum. Maybe that's oversimplified also.
Yeah, I mean, I really can truncate it to an odd number of sites in this case though, because I can say that I map the Hamiltonian, I get the Hamiltonian here, I get some weird Hamiltonian here when it gets mapped onto the circuit. But once I get far enough this way that I'm here, I know that how the Hamiltonian is mapped, it has the same ground state as the shifted Hamiltonian. So I can drop those terms in the Hamiltonian that I produce, add these ones, and then I can really just cut it off from here because I know outside here, I have I have this one and this one. And yeah, if I want to do it on a finite system, I do need to have one more site, but I cannot produce that term.
My objection was merely, yes, you can have an odd number there,
Mhm.
but to draw the conclusion you want from that, you need to know that it's part of the system with an even number, where you commute with something else, anti-commute with something else.
I have a related question. So imagine you had an odd number of sites.
Mhm.
Then you can have different things at the two ends.
Right, again, there's not really any more end here present. This is happening within some either large ring or.
So let's consider a
So we're,
finite chain.
then we're isolating this.
So there's a finite chain with
Yes.
an odd number of sites. We
Right.
can discuss the subtlety with an odd number of sites, but let's put that aside for the
Mhm.
moment. And then you have an edge mode only on one side.
Right, but right, yeah.
Would you say that this is the same phase, the same number of sites where the edge mode is at the other end or not?
No, there's no way to map from one to the other with a local circuit. You can only map from one to the other with the circuit would need to be non-local. There's no way to do that map with a
So
local circuit.
if I have a local operator that I add since there are L sites, so I add L times, would that be considered local or not?
Local circuit means order one depth this way and order one width for each gate.
And only order one's number of steps.
Yes, that's what I mean, order one depth. That's what I mean depth. So there is no way to produce that. With to go between those two you mentioned.
If I think of a finite system,
Yes, you would need to have the depth and width would need to depend upon how long your system was. So yes, if your system was 10 sites, we can work out how deep and wide it would need to be, perhaps 5, I don't know. If your system was 100 sites though, we would maybe need to make it 50 deep. And if your system was, we would not be able to have an order one depth. We'd not be able to have a fixed depth.
This forces it to be spatial.
Can you maybe use somehow the fact that here there, like in the top part, there is one state, and in the bottom there are several degenerates?
Okay, yeah. And again, though, we should imagine that this is either on an infinite line or it's a ring that closes. A ring that closes. And it's a ring that closes if it's a ring that closes, we need to keep this circuit small enough compared to it so that if it's on a ring that closes, then when I try to do this here, I'm doing the trick on an infinite line. If it's on a ring that closes and I want to do this trick with truncation, we're going to wind up producing two odd width regions between like the one phase, the other phase, and then two regions of odd width. And then you can gap it out, but you would need to have operators that couple this region of odd width to that region of odd width. But that's forbidden because the map only generates local terms in the Hamiltonian. So I feel like I'm explaining this argument badly because it's a fairly simple and fully rigorous argument, but I think I'm explaining it badly in an attempt to do it too, maybe it made too much of a hand-waving explanation, or was too careless about whether I was saying an infinite or a finite system. But another way, yes, you can take a finite system on a ring and you would then, with this argument, produce two odd width sites. And then the only way that you could have gapped it is if you had a term coupling them, but that's forbidden by the locality of your assumption that your circuit range. So you need to then make your ring large enough compared to the range of the circuit to do this argument. Okay, so these are two examples. A third example of a class of interesting topologically ordered phases that has been studied a lot is the quantum Hall state. And there's a whole family of different quantum Hall states in various dimensions. These are now topologically, they have unique ground states, so they don't have this ground state degeneracy. But there's an interesting phenomenon that in order to understand the Hall state in, say, 2 dimensions, if you have just the regular quantum Hall state in 2 dimensions, so you have some 2-dimensional lattice, you have fermions, not these Majoranas, but ordinary fermionic operators at each site. You have some short range free fermion Hamiltonian that hops these particles around. There's an interesting phase that's classified by an integer, which is the quantum Hall conductance of this phase. And Alexei Kitaev figured out a classification of these states in all dimensions, but he also figured out an interesting periodicity, how that the problem of classifying them in 1 dimension can be reduced to a problem of classifying them in 1 lower dimension. And I want to briefly mention one of the very simple examples of the periodicity he came up with, which is a map from these quantum Hall states in 2 dimensions to unitary transformations in 1 dimension. So he says, let's assume we have some Hamiltonian that's like some I and J, Aij, psi dagger I, psi j, where you have fermionic operators psi at each site. And what properties should this matrix A have? It should be short range, maybe not strictly short range, but some exponentially decaying tails. And he wanted to spectrally flatten it. Spectrally flatten is useful for simplicity. So A squared is 1. So he would have the eigenvalues would be plus and minus 1. Then having done that, Alexei said, well, what we can do is we can sort of divide the system into an upper and lower half plane. And we can do something that morally we can say is, let's write down some function f that's 1 in the upper half plane, and 0 in the lower half plane, And let's look at e to the I f times a. Now this is a little bit weird what I mean here. I'm being a little bit loose in terms of what I say because A involves 2 sites that are nearby each other. And so should I, oh, sorry, there's a pi in there, e to the I pi. Should I include, if 2 sites are both up here, then f is 1. You map each term with in this way to generate this operator that we can pictorially call f times a. Okay, if they're both up here, f is 1. If they're both down here, f is 0. We won't worry too much about exactly what we do near here. Just do something reasonable, basically. It doesn't matter too much. And because the Hamiltonian is short-ranged, the terms that are one thing far in the upper half plane, one far in the lower half plane are quite weak. So again, it doesn't matter too much what you write down. So what you wind up producing in this way is you wind up producing some operator that is the identity in the lower half plane, up to maybe a little small error because of A not being strictly local. The identity, well, a phase in the upper half plane. But along this line, it may do something. it may do something interesting along the one-dimensional line. And in fact, there's a nice map that if the original phase was some quantum Hall phase, what you produce in here, you produce a unitary transformation that lives in one dimension, a free fermion unitary, a unitary that maps, it's a free fermion unitary, so it maps psi on a site to some sum over j, psi j was coefficient. So it's a free fermion unitary, it just maps psi's to linear combinations of psi's. And this free fermion unitary has a flow to it. It moves things one to the right. So there was this nice way of taking this invariant, this Hall conductance in 2 dimensions and reducing it to a flow in 1 dimension. So the story of QCA is the story of trying to understand generalizations of these flows to the many body case beyond the free fermion case. So now finally, halfway through the talk, let me say what a QCA is. I've said what a quantum circuit is, right? A quantum circuit, and this could hold in any dimension. So let's say you have some quantum circuit unitary. What do we know about it? Well, you can define a map. If you take an operator conjugated by a quantum circuit, this will define some map that we'll use Greek letters alpha of O for the map. And what properties does this map have? Well, this map maps products of operators to the image of the product of 2 operators is going to be the product of their images. The image of the Hermitian conjugate of an operator is going to be the conjugate of an image. So we define some star automorphism of the algebra of operators, local operators, and it has a certain locality property. If O is supported on some site, alpha of O is supported near that site within some range R. So you have a certain range R. And in the case of a quantum circuit, the range R is going to be derived from the depth of the circuit and the width of each of these gates. And let's say we abstract out these properties and we require just these 2 properties, that you have some linear map to find such an automorphism and such that it spreads operators by only a certain amount. If you have an operator that's supported on a site, its image is supported nearby the site. This includes such a thing as a flow, something that maps an operator on the site to the operator on the neighboring site. That would be an example. And in fact, going back to this example, this flow, similarly here, this flow can map one of these states to each other. So the flow that shifts everything one to the right can map one to another. So such a flow is an example of a non-trivial quantum cellular automaton. A trivial quantum cellular automaton is a circuit. A non-trivial one is something that cannot be written as a circuit. And if you look at quantum circuits quantum cellular automaton modulo circuits, this actually defines some group, and it's actually an abelian group. And so the interest is then to study this and hope that this will teach us something more about possible phases of quantum many-body systems. Let me now talk about what we know about quantum cellular automata in 1, 2, 3, and then higher dimensions. More questions? So in 1 dimension, one nice example of a quantum cellular automaton is precisely a shift. You can say, okay, I map every operator, Pauli operator, if I have qubits on each site, you just map every operator on a site to the operator 1 over. And in fact, all 1-dimensional quantum cellular automata are classified as basically just being shifts. And there's some rational index for them. If you shift a qubit degree of freedom 1 to the right, the index is 2. If you shift it 2 to the right, the index is 4, and so on. If you shift perhaps a q-trit, a degree of freedom 1 to the left, the index would be 1/3. You can have an index of 2/3, which is shift a qubit to the right and a q-trit to the left, and so on. And that's the full classification. How do we know what this classification is? Well, take some interval I, and let's let A of I be the algebra of all operators on that interval. And to clarify again, on each site, there'll be some dimensional degree of freedom, perhaps a qubit or some higher dimensional degree of freedom. So there's some Hilbert space on each site, and we're not going to talk about fermions now. We'll just assume some qubit or some such on each site, and the full Hilbert space will be the tensor product. And now you can look at the algebra alpha of A of I. The image of this algebra under your under your QCA. Well, what do we know about that? Well, it's contained, let's draw some slightly bigger interval, I greater. That's contained within the algebra on this larger interval because of this locality property. Things can't expand too much. On the other hand, if I drew some slightly smaller interval like that, I conversely would have that the algebra on the slightly smaller interval is contained with the algebra on the interval. Sorry, I've done.
Not to have some of these alphas?
Yes, sorry, I was just realizing I did not mean to write that alpha in that one, thank you, yeah. I did not mean to write that one, yeah, alpha of this is contained within that, of course, otherwise it's true. And alpha of this is contained within this one. Sorry, this one is contained within that one. Yes, now I've got the right alphas. This one is contained within this one. So when I take this interval and I map it under the QCA, take this algebra and map it under the QCA, I get the full algebra on this interval is included in there. Why? Because if you have any operator on this smaller interval, you can inverse map it under alpha. That will be supported nearby because the inverse of alpha has the same range as alpha. And so it'll be supported on this interval. So if I take alpha of AI on this interval, it contains all of these and it's contained in this slightly bigger one. And in fact, you can then show that this triple alpha and A look too similar. Alpha of AI is the smaller interval algebra, the algebra on the smaller interval, tensored with two other algebras. Tensored with some, I'll call it alpha left and alpha right. Some algebra on the left and some algebra on the right, which is supported near this end and supported near this end. You may worry, oh, maybe somehow like this algebra is in some way, like things don't factorize between them. It's possible to show, no, things do factorize between the left and right. I won't take the time to show that, but it's not good to show. And since this algebra is simple, simple meaning has no center, this algebra and this algebra will also be simple here. So what does this algebra of operators is, the image of the algebra here is going to be this full one, something on the right, something on the left. And the dimension of the algebra has to remain the same under this mapping. So that imposes some constraint on how big the dimension of this left algebra is and how big the dimension of this right algebra is. And essentially the index is, and so one of these dimensions can go up at the cost of the other one going down. And essentially this index is how much bigger this dimension is than this dimension. So if you take this shift thing, you'll find that, say, this dimension has increased. You've moved basically, you had first the algebra here, and then you interval here, then you shifted it to there. So you have a little bit bigger algebra on this side and a little bit smaller one on that side. So the index just counts it. It's the only invariant you could have for just some matrix algebra. Is just one dimension, is some simple matrix algebra is just one dimension. So that's the full classification of QCA in one dimension.
So that argument would suggest the index is an integer.
It's a ratio of yeah, it's a ratio of two integers. Because it's one dimension divided by another dimension.
Okay.
And so it's some rational. Okay. So it's which is just reflecting like, oh, you moved it left or right.
Okay.
So that's 1D. When you go to two dimensions, so 1D is fully classified by shift. 2D, there are none. Or let's say no non-trivial. All QCA in 2D are trivial. Depends a little bit how you define what trivial means, because I was saying you define it as trivial up to, something is trivial if it's not a circuit. And you may say, oh, well, what about if I have like a large 2D plane and somewhere in the middle of the 2D plane, I have a shift going along a single line. Isn't that non-trivial? You've got a shift. So we actually slightly broadened our notion of non-trivial, or of trivial, which was either it was trivial up to shift, or we talked about a blending equivalence, which is, could you draw some large region and make it look like the QCA in the large region, and then look like the identity far outside the large region and blend between them on the boundary. And then in this case, you can blend this shift into the into the identity outside. So so this is blending equivalence with blending. Let's use the notion. So I will spend a brief amount of time explaining why 2D QCA are why there are no non-trivial 2D QCA, and then get to 3D, where, I mean, obviously, if the punchline is that they stayed trivial in all dimensions, this would not be as interesting a subject. And 3D, there are lots of non-trivial QCA. And they are associated with the creation of various interesting, and 3 and higher. They're associated with the creation of lots of interesting non-trivial invertible phases. Invertible phases of the form that are, they're not these topologically ordered ones like the toric code that get a ground state degeneracy. These instead are ones that get, that have some interesting action on interesting space-time manifolds, but that have a unique ground state always. So if I sketch the argument, just to take like, this would be very brief, so probably it doesn't make sense, don't pay too much attention. Why they're non-trivial in 2D. Here we talked about sort of some algebra gets produced at the right and the left of the interval. Now suppose we had, say, an annulus. And so let's just draw some 2D region and imagine that you, well, you know, let's say you have a cylinder, so you like this. So you have some two-dimensional region, and you have some sites on the cylinder like this. So you can just top and bottom of this are joined to make an annulus. And you try to play a similar trick. So you take some interval and you look at the full algebra of operators on this interval, but it's only, you know, it's got a left boundary that's a circle and a right boundary that's a circle, joining into an annulus. Now you try to play the same trick. Well, you'll generate some algebra on the right edge and some algebra on the left edge. And you want to study what is this algebra on the right edge. It's some algebra that lives in one dimension. So there'll be some one-dimensional line, and you'll have some interesting algebra of operators that essentially the QCA is transporting this algebra of operators in this direction. Now, what property does this algebra of operators have? It has a certain property that we call visibly simple, meaning not only is it a simple algebra in the sense of having no center, but that it's somehow easy to see that it's visibly simple, meaning that if you have any operator in this algebra, any site in its support, there's something nearby that doesn't commute. To explain that definition, I give an example of something that's not visibly simple. Suppose you have the algebra generated by XX on these two sites, ZZ on these two, XX on these two, ZZ on these two, and so on, and you finally ended with the ZZ. This is a simple algebra, but if you wrote down then the operator X, 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 and so on, and you said, oh, I want to pick something in the middle of it, it kind of is like a string operator, and in the middle of it, these ZZs all commute with it. You need to have something near one of the endpoints to see that this algebra is not simple. So there is this notion of visibly simple algebra, and using the locality of the QCA, you can prove that this right algebra is some visibly simple algebra in 1D, and then by some structure theorem for those visibly simple algebras, you can prove that they all take some particularly nice form from which you can then show that these 2D QCA are all trivial. But now let's get to 3 dimensions, 3D QCA. And the first non-trivial QCA ever that wasn't a shift comes from an interesting model called 3-fermion Walker-Wang model. 3F. Walker. F is for fermion, Walker-Wang. Walker and Wang are Kevin Walker and Zheng Wang, and 2 mathematicians. So this is a model in 3 dimensions. And just like in 1 dimension, I mentioned these 2 states of a Majorana chain, the trivial and the Kataya phase, and said, well, there's a QCA that's the shift that maps between them. This 3-fermion Walker-Wang model is going to describe an interesting state in 3 dimensions, and there's going to be a QCA that maps that to the trivial state, a product state.
Did you say that Wang is a mathematician?
Yes, Zheng Wang.
Was he one of the tilings? Did he work with tilings or not?
No, he's a topologist.
Topologist, okay.
Yeah. in order to explain this three fermion Walker-Wang model, I should explain the 2D three fermion TQFT, that was field theory. So I mentioned at the start that there was this nice example of a topological ordered phase, the toric code, and it has some excitations which are anyons. There's this electric anyon, there's this magnetic anyon, they braid non-trivially, and you can combine the electric with the magnetic to make a composite, which is a fermion. So it has two bosons and one fermion, and they all braid non-trivially with each other. So if one goes around one of a different type, there's a -1 phase. The three fermion one has three anyons, just like the toric code. If one goes around one of a different type, there's a -1 phase, just like in the toric code, but they are all fermions. That's why it's called the three fermion model. They're all fermions. You may say, okay, I wrote down a Hamiltonian, or I at least sketched a Hamiltonian for the toric code. Will I write down a Hamiltonian for this one? And the answer is I can't. I mean, you can write down one that is in terms of some non-commuting terms, but you cannot write down one in 2 dimension that is in terms of commuting terms, but you can at least talk about it as a theory. And it actually can live at the boundary of this. So this thing is some model, and you should just imagine that, okay, there's these point-like particles that have this interesting braiding. The Walker-Wang model is essentially, its ground state encodes how this model works. So if the Walker-Wang model, you have two cubic lattices in 3 dimensions, very slightly shifted from each other. And then on each link of the cubic lattice, you have 2 possible states. And so when you look at the 2 links near each other, they can form 4 different states. Well, we say 0 or 1 on each link, so it can be 0, 0, 0, 1, 1, 0, 1, 1. All the ones other than 0, 0, we'll say that that's like there's one of these 3 fermion anyons present. And so a possible state of this Walker-Wang Hilbert space will look like some strings of these fermions in 3 dimensions. And there's a penalty term, just like there was a penalty term in the toric code that said they shouldn't end. There's a penalty term there that says they shouldn't end. So all the states that are ground states will be some, and they'll be labeled in some way F, G, there's 3 types F, G, and H. So they'll just be like little bubbles and loops of these things in 3-dimensional space. The ground state will be that. And then just as in the 2D toric code, there was some term to move them around, in the 3 fermion Walker-Wang model, there's some term that nucleates bubbles of these and allows them to move through 3 dimensions. And it's chosen such that if you pick any configuration of them in 3 dimensions, its amplitude is whatever that 3 fermion TQFT in 2 dimensions assigns to that as a space-time history. So like the ground state of this encodes all possible space-time histories of that. So for example, here I drew an F and a G linking each other. So this is going to have a minus sign in its amplitude in the ground state. It might have some other minus signs because you have to figure out what framing we put on these, and so there will be some other minus signs. But this will have a minus sign in its ground state because I drew them linking each other. And so that's what determines the amplitudes in this 3 fermion Walker-Wang model. And one of the interesting things about this 3 fermion Walker-Wang model is that if you take it on a, say, a sort of a slab, and if you want, you can make the top of the slab, say, be a, it doesn't need to be, so this is a 3-dimensional slab, but perhaps let's connect the boundaries of this top, so the right to the left, the front and back, and the same on the bottom, so that we get some 3-dimensional geometry, which looks like a torus in 2 dimensions crossed an interval in the 3rd dimension. Then, if you write down this 3 fermion Walker-Wang model, it supports in the bulk, then you can write down its terms, but then when you get to the boundary, you have to decide how you're going to truncate it. You have to figure out how you're going to truncate it. And it turns out that the way you can truncate it with local terms, you can now truncate it at this boundary with local commuting terms, and you'll produce this model at the boundary. So this 3 fermion TQFT doesn't live on its own in 2 dimensions as a local commuting term, but it does live at the boundary of this 3 fermion Walker-Wang model as a local commuting term. But then there has to be another boundary. And so now you can make the same kind of argument as in 1 dimension. There cannot be a quantum circuit that disentangles this 3 fermion Walker-Wang model, or at least that most strongly maps the 3 fermion Walker-Wang model Hamiltonian to just the trivial Hamiltonian, which is a sum of Pauli Z's. Because if there were, we could take this 3-dimensional slab and we could the circuit, let's say, of course, exists maybe arbitrarily far, but we could do the circuit sort of here and up, or let's say here and down. We could do the circuit here and down. And we don't really know what's going to happen at the bottom layer because we have to get rid of the circuit at the bottom layer. But at least below this halfway through cut in the slab, the Hamiltonian has turned into the all Pauli Z Hamiltonian, because that's the assumption as to what the circuit does. We can then drop the other terms that are the image of this Walker-Wang model into the circuit, because we don't know what the circuit's going to do at the bottom boundary, and just attach Pauli Z terms down there. So we've turned the Hamiltonian down here into all Pauli Z. We've left gap one. Then we don't do anything up here. So we still have the three fermion Walker-Wang model up here, and then we terminate it with a way that we explicitly know how to do this three fermion TQFD at the top boundary. And so what we would have written down then is a two-dimensional model. Yes, there's a third dimension, but we don't need to take that third dimension very big. We only need to take it a little bit bigger than the range of the circuit. We've written down a two-dimensional model, so then we just forget about that third dimension. We've written down a two-dimensional model with local commuting terms that supports this kind of topological order, which everyone believes is impossible. So it's essentially the same argument as to why you can't do this shift between these, why you can't find a circuit that maps these two shifted states to each other. So
Sorry, the argument is that this topological quantum field theory in itself doesn't make sense, but
Right.
all this makes sense.
right now, that's an assumption. So you can, you have to. That's very strongly believed that you can't have that on its own in two dimensions with commuting terms. But if you assume that, then you can prove that there's no way you can map this three fermion Walker-Wang model to the disentangled.
Sorry, can you repeat the question?
I think the question was is it an assumption or not that this model doesn't exist on its own in two dimensions, at least with commuting terms?
When you say model, do you mean a continuum field theory? Or do you
Or no, I mean, does there exist some local Hamiltonian with commuting terms? Yes.
Why does it have to have commuting terms?
Yeah, well, okay, so why does it have to have commuting terms and strictly local terms? So these maps will map the original terms which commute to each other with new terms which commute with each other. And then, because the map is a unitary map, and then the way we explicitly add in those terms at the top boundary, we know keeps it commuting. So if this circuit could be, if this Hamiltonian could be disentangled by a circuit, then there would be commuting terms. Now, there may be a way to form it with non-commuting terms. I mean, essentially the obstruction to forming this with commuting terms is that it has some chiral central charge. So it should not be possible to produce that with commuting terms, but I don't know a real proof of this. Like, I mean, there's a physicist proof, but I don't know what math proof it is not possible. So you have to make an assumption that there is no way to produce this. But if you assume that, then we can make it a little more technically precise as to what it means to be in this phase. Like it has certain string operators that commute with the Hamiltonian and have certain relations with each other, and those are the only non-local string operators in the theory and so on. But yes, you have to assume that, but then it follows that there is no way to generate this phase.
Just to be clear, you are not claiming that this model does not make sense as a 2+1 dimensional field theory.
No, it makes sense. You just, if you want to realize it on the lattice with commuting terms, then you have a problem.
And can there be a lattice model with all sorts of excitations and that leads to these effective TQFT at low energies? Would be entirely
If it has some, yeah, I mean, if it has some commuting terms, probably, non-commuting terms, probably, yeah. Because you should be able to then like add on something like a Hall effect to cancel the central charge, and then in that way obtain something where there's no obstruction to building it. So it should be possible if you allow more general Hamiltonian. And so this is all in the framework of, also if you allowed sufficiently long tails, it may be possible with commuting terms. This is all in the
Why
framework.
is it so sacred to have these computing terms? I understand why we like it, because then we
Oh, yeah, okay, no,
It's
it's
not a principle of nature.
no, it's certainly a nicer class of Hamiltonians to talk about. And it's not, that restriction to commuting terms is not coming from, like, I'm not imposing it. I'm talking about QCA. And then since we have these QCA, we say, oh, if this QCA were trivial, then we would have something with commuting terms. So it's coming for free almost. The thing that's an assumption I'm making is that I'm also strictly cutting, or the way I'm really talking about restricted areas, I'm really saying my QCA are finite range instead of having some tails. And it's kind of subtle to add tails in. It's kind of only starting to be understood what tails do in 1D. So you might also ask, okay, what if your QCA is like not strictly local, but it obeys some like weaker assumption of locality. So the image of an operator is approximately supported nearby. And even in 1D, it depends like what norm you take for how close to, how you define it, approximately local, and nothing is known beyond 1D.
Maybe I should reverse the direction of the question. What do I learn about the TQFT from the fact that you cannot have this construction?
What do you learn about?
So there are two worlds, the TQFT world and the lattice model. And I think what you said is in one direction. I'm asking, what can you learn in the other direction?
I don't know. I mean, I guess what you already knew, that it's chiral is, I don't know that there's a specific new thing that you learn. Yeah. We're importing knowledge rather than exporting knowledge at this point. So I just have a few minutes. So let me just sort of say, I said lots and above 3D. So let me just kind of like, this 3 fermion QCA was constructed in a paper with myself and Fidkowski and J Haah now, I don't know, like 6-7 years ago or something. We constructed it some time ago. And I wonder if people are gonna say, you 3 are still thinking about the 3 fermion model. How are you not done with this? But we have continued to work on this and found a number of other things. And we recently found a kind of construction. Our original construction of this 3 fermion QCA was rather complicated. It was found partly by computer algebra, taking some explicitly finding, this is exactly the mapping that takes this form and Hamiltonian disentangles it. But later we were able to come up with a much nicer way of writing it, which was, we looked at another Walker-Wang model, a Walker-Wang model that, the 1F Walker-Wang model that has some fermions coupled to a gauge field and emergent fermions coupled to a gauge field. And we took 2 copies of this and then said the QCA is simply -1 to the linking number of the 2 gauge fields, the gauge field on copy 1 with the gauge field on copy 2. It was almost immediate that this was a QCA because any local operator can only sort of locally move one of these gauge fields around, and you can then locally compute whether it changes the linking. In this way, you can then also show that you produce the 3 fermion ground state. You can do something that's kind of like completing the square to shift out one of the gauge fields and verify that this linking of the 2 gauge fields turns into essentially binding type 1 gauge field to type 2 fermion, which now causes type 2 fermion to braid non-trivially with type 1 gauge fermion because you've bound the type 1 gauge, binding type 1 gauge flux to type 2 fermion, which causes the 2 fermions to braid non-trivial each other and produces this 3 fermion Walker-Wang model. And then once we thought of that, we then sort of immediately, well, not immediately, a year or 2 later, played the game of generalizing to higher dimensions and more gauge fields. And we constructed a family of models constructed in different levels of detail. Some are constructed exactly on lattice, some are like, this should exist on lattice morally for these reasons, but we haven't written it down in detail. But instead of say point-like fermions in 3 dimensions, you could imagine point-like or line-like or something like fermions in more than 3 dimensions. And you could have several such things. So instead of being linking of gauge field 1 with linking of gauge field 2, you could have linking of gauge flux 1 with linking of gauge flux 2. You could have something like 3 different gauge fluxes and say linking of gauge flux 1 with the intersection of gauge flux 2 and gauge 3. And in this way, we were able to construct a whole family of these QCA. And we believe now that, I mentioned that this Kitaev chain had a particular action when you consider that on a non-trivial manifold, this W1 squared. We believe that we can construct any, an invertible phase that has any action in terms of Stiefel-Whitney classes on any manifold. So there's some philosophy due to Kapustin that the way to classify these invertible phases is their actions on different manifolds, and that if there's a time reversal symmetry present, then it's expressed in these terms. And we believe we can now get QCAs that produce every single one of the phases in his classification and disentangle them all. So there's some interesting relation emerging between these QCAs and possible invertible phases. There's some that I sort of really hope will happen, but has not yet happened. Like one of the original motivations was this kind of descent that you could start with a 3D Hall state and turn it to a 1D shift, a 1D free fermion QCA. And then in the free fermion case, it's known how to keep going. You can then take it. Of course, in 1D, it's easy, but if you started with some very high dimensional Hall interacting fermion, hopping free fermion model, you could turn it into a one lower dimensional unitary on those fermions and then turn it into something in one lower dimension, something in one lower. So it's known how to keep going. We don't really know how to keep going with QCA. We have this notion of like, we can start with the QCA, we can turn it into some boundary algebra in one lower dimension, but we're trying to understand how to go further there. Some periodicity has been found for special cases, but not in general. So let me stop here and take any more questions.
Yeah, could you say anything about this Kapustin construction?
Yeah, well, Kapustin had this conjecture that you could classify invertible phases of matter. And with or without symmetry, and then presence or absence of time reversal symmetry. So in the presence of time reversal symmetry, his argument was that they were classified by looking at a space-time manifold could then be unoriented. So they would be classified by unoriented cobordism group of space-time manifold in, well, d-dimensional phase, so on a d+1 dimensional space-time manifold. So in this case, for example, the Kitaev chain had some action W1 squared. This 3 fermion model has some interesting action W2 squared on a 4-dimensional space-time manifold. Yeah, so you might be wondering a little why I was talking about time reversal symmetry, because time reversal symmetry played no role in here. So we have a guess that our guess is all these QCA we're constructing, we think they, we don't have, especially when you go beyond 3 dimensions, we don't have a proof they're non-trivial. We just conjecture. So, and even then in 3 dimensions, to show it's non-trivial, we had to rely on an assumption that the 2D TQFT, that this particular 2D TQFT cannot be realized on a lattice in a certain way. So even that relied on an assumption.
You have to assume that.
You have to assume that. I mean, it's very, very strongly believed, but you have to assume that. But so then it would be, if we believe Kapustin's classification of these as invertible phases, then at least our QCA are non-trivial with time reversal imposed. There's no way to find a time reversal invariant decomposition as a circuit, even though they themselves are time reversal invariant. We have a further conjecture, which is that if there's an if there's a orientable manifold that detects this, so for example, W2 squared can be detected on an orientable manifold, then the QCA will be non-trivial even without the time reversal symmetry, but that's just a conjecture. It's just sort of a nice guess that happens to be correct in 3 dimensions, but we don't know if it's true beyond there. So yeah, some stuff lines up, but we don't fully understand when these are not trivial. Yeah.
You described the Walker-Wang model as a Hamiltonian model in 3 space dimensions.
Yeah, I mean, it could be written, there's a variety in different numbers of space dimensions, but yeah.
Well, for the particular case of the 3 fermion model.
Yeah.
But then you assert that in 4 dimensions it has this action W2 squared.
Yeah.
For that statement to be meaningful, we need to know how to define the theory on a general form manifold.
Yes.
Whereas the Hamiltonian description didn't tell me that.
Yes, and this is something that people have worried about because, and in fact, you could imagine different ways of defining it on a 4 manifold that produce the same 3 fermion theory, but that sort of actually change the action and it's not always W2 squared. So there is some argument by Xiaogang Wen that there's a particular branching independent requirement you need to impose on how you define it that will allow you to define. No, this is something that's bothered me, and I think bothered a lot of people in thinking about these, that when you say this W2 squared, it's, or whatever you say, it depends upon how you extend it to the 1 higher dimensional space-time manifold. So there have been some proposals that, okay, that if the extension is defined in a particular, you have to show that it exists. And then you also have to argue that, okay, is the phase really going to be independent of how I extend it to the space-time manifold? So there's also some statements, well, then the extension should obey a certain branching independence. I don't have much to say about it because I feel that that's not well understood in the field, what you need to do. So
But at a more basic level, I don't know why this three fermion model extends to a four-dimensional theory.
why does it extend to a,
You started with what was really a 2+1 dimensional theory.
yes,
That gave expectation values of what physics in relativistic field theory would be.
mhm,
Then you took the expectations of all possible Wilson operators
Mhm.
to be a functional
mhm,
of, well, then Walker-Wang cook up a Hilbert space and a Hamiltonian,
yes,
such that allowed vectors in the Hilbert space, at least those of finite energy,
mhm,
correspond to configurations of Wilson lines.
mhm,
And the ground state wave function
mhm,
is the expectation value
mhm,
of the product of Wilson lines.
mhm,
So I can see how that construction would work.
mhm.
But why that's part of a four-dimensional theory?
Okay, I mean, there is written down for at least this, I think, there is written down though, I mean, it has been written down in explicit 40 version. You need to, it would be better to talk to someone like Chern-Simons or someone who can, or Kevin Walker. But there are, some of these four-dimensional states, some things do give these three-dimensional Walker-Wang models on their boundaries.
I think I can, if you continue with this, I think enough to answer this question, not
Yes,
about
okay.
QCA. The model we're talking about in the language that I'm happier with is spin 8 level 1. So the three fermion model is what we would call spin 8 level 1.
Mhm.
And that model has some one-form symmetry and it has an anomaly. And the anomaly theory for that one-form symmetry is the four-dimensional field theory. And
I'm fine with that, but I thought we were told that there's actually a four-dimensional topological field theory. Whose
I
Hilbert
thought
space
you
is
wanted,
three-dimensional.
sorry, I thought you wanted an invertible theory, 4-dimension, whose boundary is this three-dimensional field theory.
Well,
Its boundaries should realize this ground state. This is the,
it's that statement that puzzled me. The way Matt just said it.
Sorry?
Although I don't know the details, I'm not that surprised that there's an anomaly theory in 4 dimensions, that's W2 squared. I thought the claim that was being made here was that this Walker-Wang theory is really the Hilbert space version of a true 4-dimensional TQFT. And I don't know why that would be true. If that's the claim, I don't have any idea why it would be true.
I think there is a concrete 4-dimensional state sum that gives this to you. I gotta check it, but
Well, what Danny said is different from what I understood from before, perhaps I misunderstood. What Danny's saying is that there's this 4-dimensional theory that's anomalous on a manifold with boundary. And something it could have on a manifold with boundary is the three fermion theory. But I have trouble matching that with what you told us, which sounds like a stronger statement.
yeah, I'm not sure. I'm just saying there is a 4D state sum that has this. But I cannot write it down off the top of my head right now. But I know there is.
I'm a little confused, perhaps you already said this, but so I understand the phase of matter to be a property of a state, right? The QCA is a property of this operator algebras.
Yeah, it's a little bit.
How are you imagining that this discussion of QCAs will be useful for classifying?
Yeah, it's a little bit of a stronger thing than a state, in a sense. I mean, exactly what you say. There's in between us first having the incredibly complicated QCA found by computer algebra that disentangles the three fermion Walker-Wang model, and then the much simpler version here, we had a separate existence argument that it exists for the theory that allowed us to more simply show that it exists without actually writing it. And this was based on what we call a separator. So what is a separator? Well, a separator is going to be a bunch of commuting operators, each takes eigenvalues plus minus 1 with no redundancies. So that every time there's exactly n sites, there's exactly n such operators. And if you look at the eigenspace of, a certain number being +1, certain number being -1, if you fix the eigenvalue of L of them, it cuts the Hilbert space by 2 to the L. So each of them is just cutting the Hilbert space in half every time you. And we define locally flippable separator meant that there was some operator that flipped each of these terms. So the separator terms should be local, and there should be some local term that flips them. So if you take the Walker-Wang Hamiltonian, this has some redundancies in it. It's a stabilizer Hamiltonian, the 3 fermion one at least. You can write it down explicitly as a sum of products of Pauli's. But the way it's typically written has some redundancies. Certain terms in the Hamiltonian are redundant with other ones. The products of these terms is +1. But you can find some rewriting that has the same ground states, but has fewer redundancies, has no redundancies, so that the new terms give a separator. And in fact, they give a locally flippable separator so that they can be flipped. And now, so if you sort of say, well, let's say Z tilde I is a separator term, and X tilde I is the flipper. It flips the value of Z tilde I, but nothing else. You can guess, maybe there's going to be a QCA that simply maps ZI to this and XI to this. Now there are two, it seems like it's an algebra. Now there are two things you need to worry about. First is pairing each Z with a Z tilde I. Like, are there going to be separator terms near Z's? And you can show that there are using, for example, the hall-Marx theorem, or you can explicitly construct it in this model. And then another worry is, well, the flipper flips this term, but it's possible that the flipper flips this term but picks up a phase that depends upon some of the other ZIs. So it might be that real I should map XI to XI tilde like ZJ, Z tilde J or something like that. But you can show just with the locality that this is locally flippable, that you can correctly absorb those phases. So this gives a mapping. So as soon as you find this separator, you've defined the QCA. So once you have a Hamiltonian, but so this is exactly, this seems like a bit of a digression, but this is exactly kind of your question, because this is something stronger than having a state. It's like saying we're mapping not just the ground state, but an entire, we've identified some decomposition of the Hilbert space into 2 to the n different states. And we're mapping every single one of them. So one of them, which is the ground state, is going into the product state, but then we've identified some decomposition of the excited states such that each of them maps into a ground state with a certain number of spins flipped. So yeah, this is stronger. And so you may wonder, are there going to be cases where, the states can be mapped, but the full spectrum cannot be mapped this way? And it seems possible as just an abstract possibility, but we don't know an example where it's meaningful.
There's no other questions. Let's thank Matt again.